what we're going to do during most of our classes is going to kind of look like this. So you'll notice it's kind of notes, but there's a lot of holes in it too. And the idea is that we'll kind of work through it. So yeah, so you're going to actually be working every day instead of just sitting on your butts. Anyway, today basically what we're going to kind of do is sort of motivate what at least a significant chunk of calculus is all about, which is to say rates of things, right? So what did we learn in the warm up? Let's just start there. Well, don't jump up all at once. Okay. Yeah. So what's the idea of a derivative? Just big picture. Yeah, rate of change at an instant. Okay, as opposed to an average rate of change, right? So what's the difference between those? I mean, other than one's at an instant and the other's average, which is what I just said, right? Okay, but yeah, so like if we drive someplace, let's say we drive to Indy, it takes us an hour, and it's 60 miles to Indy, roughly. Then what's the conclusion? On average, right? Does that mean that my speedometer read 60 miles an hour the entirety of the trip? No, because what's it probably going to be reading between here and getting on I-74? Yeah, lower than that, right? Because I'm in the city, and then I get out into on 32 or whatever, and it's the speed limit's like say 55, or there's that part where it's 45, and there's always a speed trap, and right. So it's not that as if my speedometer is reading 60 miles an hour every single instant along the way. And then, of course, if it's going to be below 60 some of the time because I'm not yet on the highway, then what's got to be true on the highway? It's got to be above 60 so that it averages out, kind of thing. And that makes sense, right? Because on the highway, right, I'm usually doing 75 miles an hour. Um, Yeah, roughly. Okay, so makes sense, right? That sort of distinction. So calculus is all about the instantaneous, what's happening at one instant in time. Okay, and algebra will allow us to do these averages, right? And if we combine the two, then we can do all kinds of interesting stuff. Okay, so anyway, so let's take a look at this sheet here, and we've got this thing and there's plenty of room at some of the chalkboards. So if somebody you want to hop up the chalkboard, great. If you're going to sit, just buddy up with somebody. Yes, what did I screw up? Oh, well, then I guess you just fail. Um, or all of the people sitting around you fail because they failed to give you one. Yeah. All right. Everybody else has one. We're Gucci. Okay. All right. So let's suppose that we have this sort of shape over here at the right, which is, like imagine it's a flask or something from chemistry. Um, and let's imagine that I'm filling it with a liquid. Okay. So what I want to do is I want to think about um, as I'm filling this thing. Okay, as I'm adding volume to it, what's the height of the liquid? Uh, okay, so right, what would be at h of 0? Okay, before I start putting any liquid in. Yeah, an empty bottle. Okay, so we'll say that the height of it above the bottom of the glass is 0, right? Because I haven't put anything in yet. Okay, and then let's say that the volume of this contraption is 3 units, whatever those are, okay? Um, what would H of 3 mean? The bottle's full, okay, and it would be whatever the height of the bottle is, okay, however tall it is. Okay, so those 2 points are sort of easy. It's the stuff in between that's more interesting, right? Okay, so think about, and those of you who are sitting alone, buddy up with somebody. Okay, you're never allowed to sit alone anymore. Okay. Think about what's the in-between part going to look like, okay? So the idea here is we're adding a constant amount of volume per unit time, okay? So like I turn on a sink or something and the water is coming out at a constant rate. I'm not like dumping it in at first and then doing a trickle for the rest of it. Constant rate of volume, okay? Now the other thing is if we're going to make a graph here, what do we have to think about in terms of our graph? Like if I draw a graph, what do I need to make sure to label? Yeah, I need to label my independent, my x-axis, and my dependent, my y-axis. Now, what's the dependent variable here? Whatever the height is. Okay, so it starts at 0, it ends at whatever the height of the bottle is. What's my independent variable? Volume of liquid. Okay. Could we also make the independent variable time instead? We could. Okay, but we'll just do this with volume for sake of simplicity. Okay, so does that kind of make sense? All right, so think about it and start sketching what the curve h of t is going to look like, and then we'll come together and chat. Okay, is it going to be a straight line? First off, no, most certainly not. Okay, so does the question make sense? Yeah. All right, so let's see what you get. While I draw it. All right, so what's today? The 21st. Okay, so what do we kind of think here? It'll take a minute or so. Oh, while you guys are doing that, last call. Last call on what? There's going to be a party at 3 o'clock this afternoon in the Allen Center. Yeah, and we're even going to be doing shots at this party, right? Of that sweet, sweet Pfizer juice. A second booster? I don't think those are yet authorized for anybody except people who have like immune system conditions. Yeah, just like every day, go get another one. Yeah, yeah, it's probably not a good idea. So yes, if you have not already signed up, email Susan like right when class ends. And I look forward to seeing all of you there, or some of you there maybe, because I imagine some of you have already gotten a booster before you came back. Yeah. Okay. Oh, good. Yes, sir. I am not, because I do not know how to do that. Uh, well, I can't imagine it's that hard, right? Uh, no, so I will not be administering them. I will be doing paperwork and registration, that sort of stuff, right? So, uh, filling out the cards with the lot number, putting in the computer, which arm did you get it in, making sure that you are who you say you are, and your date of birth matches, and all of those sorts of things. So no, I know many things about many things, but that's not one of them. So candy? I don't know, actually. I would hope so. And and if not, maybe I'll go find some candy just so that it can be handed out, right? Well, I don't know. I mean, you can get like a Avengers Band-Aid, uh, or or maybe they'll have like Little Mermaid Band-Aids or SpongeBob Band-Aids. I don't know, right? I mean, those are pretty sweet, right? So, yeah, yeah. So, all right. So, what do we think? What kind of rough shape would we expect? And in particular, what's going to be kind of the slope of this thing right when I start filling it? Huh? Yeah, it's going to be increasing, and that makes sense because I'm filling up the thing. But is it going to be shallow or really steep? Okay, why? Okay, but then it's going to start to slow down. Okay, and then when is it going to be at its sort of slowest rate of filling? In the middle. Okay, so what I would expect is that let me sort of label a couple of points here, 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 and then say here, right? What's going to be the case between the red and the blue dot? Okay, as I move from the red to the blue dot in height, what should I expect my curve to be? Start to get steeper or less steep? Less steep, okay? And that makes sense because there's more area, which is to say more volume, and it reaches the most right in the sort of middle of the bulb part. Okay, does that make sense? Okay, from the blue dot to the black dot, what should we expect to see? Kind of the reverse, right? Where it's going to go more slowly at first, but then speed up and hit its maximum at the blue dot. Okay, does that kind of make sense? So that would be something like, oh, I don't know. Let's see how we should do this. Let's say that the black dot is here, okay, and then it should go steep until the blue dot, and then slow down, and then kind of do like this. Would you guys say that's roughly good? Yeah. Okay. What about from that point on? What's it going to look like? Okay, so after I've filled it up to like here. Yeah, a straight line. Okay. And so it might be something like this, right? Okay. Why is that? Should that one be a line? Yeah, the width is constant, right? That's the thing that kind of determines the volume per uh, time, right? So, I mean, it's a cylinder, right? You fill up a cylinder, it's going to fill at the same rate no matter where you are in the cylinder base or the top part. Okay, does that kind of make sense? Um, okay, so, I mean, this is kind of a crude sketch, but do we sort of roughly speaking get the idea? Yeah. Um, okay, great. Um, Anything else that we should kind of observe here? Well, maybe one thing to mention is if we were to try to come up with an equation for this, what kind of functions might we need to use? Or like how would we build an equation for this sort of thing? Well, really, how many equations am I going to need? Probably two at minimum, because I've got whatever's going on here, and then separately I've got whatever's going on there. So what happened? What do we call this when we sort of build an equation out of two other ones? A piecewise function? You guys remember those? Yeah. Okay. So if we were to write down an equation for this, we'd need to do some sort of piecewise function. Okay. Um, okay. So does this kind of make sense? Right. So this thought process of rates and maximums and minimums and whatnot, that's kind of the game for, a good chunk of calculus. Okay. Um, okay. Now, if I change the shape of the bottle, then obviously this is going to be different, right? So let's take a sort of second example and just sort of think through it real quick. Um, I mean, I know none of you guys are old enough to have. Why is the screen not working? There it goes. Okay, to have enjoyed one of these, but got to have the olive in there, right? Okay, so you're drinking a nice martini. Okay, so what would be true about the volume if I drink at a constant rate? So, like I've got a little straw in it or something. What's going to happen to the height of the liquid over time? Yeah, it's going to go down, and that makes sense, right? But what's the shape going to be? Start off gentle and then speed up the closer I get to the bottom of it. Okay? Does that make sense? Yeah. I don't know. It's not just martinis. I guess like some places use cups like that for their margaritas. Uh, I usually get a nice margarita at El Charo every Tuesday because Tuesday is burrito day, and so they got burrito specials. And not that any of you are 21. I don't know, Patrick, are you 21 yet? In April. Okay. Well, in April, you can go to El Charo and get an El Charo margarita, and it's a good margarita. So, anyway. Okay. So, yeah, roughly speaking, like that. Um, okay. So let's look at the next thing here, which is didn't we kind of just notice that there was a relationship between the cross sections area of the bottle and the steepness of the graph that we produced? Does that kind of make sense? Okay, so what did we notice? That the wider points corresponded to gentler slopes, and the narrower parts corresponded to steeper slopes. Do our two graphs here satisfy that property? Yeah. Okay. Why is that property true? I mean, it kind of just makes sense, I guess, right? But yeah, like what is it that? Well, I don't know. I mean, maybe it's obvious. What do you guys think? Yeah, so, okay. Anyway, but the slope here is, of course, what we're really worried about, right? And so half of calculus, we're really going to be worried about slopes. okay, in some way, shape, or form. Okay. All right, so does that kind of make sense? All right, so let's flip over here to the next one. And let's kind of think about this in reverse. Okay, so in the previous two problems, what did we think about? We thought about given a bottle to produce the graph that goes with it. What about if I wanted to do the opposite process? Okay, so draw a straight line graph. Okay, whatever slope, it doesn't matter. Then what I want you to do is think about the bottle that might go with it. Right, so you're sort of thinking backwards here. Okay, and be creative because it's not just a cylinder. That would work, but that's not the only way. Hmm? No, it's a valid answer. It's just not the only valid answer. Yes. Yeah. Popsicle tube filled with liquid. Okay, that works. A can, a cylinder, right? Those are basically all the same thing. But those aren't the only shapes that'll do it. So try and come up with another one that's not just a cylinder. Yeah.
Could you do just like a cube or something?
Yeah, actually. Okay. A cube, a box, anything like that would have the same property. It just would be square shaped instead of round shaped. Okay, that works. Okay, but even more creative than that. Yeah, that's still a cube or box, right? But yeah, I could get a baking pan, huh? I could. Probably not going to be putting water in it unless I'm setting up a double boiler to, melt chocolate or something, uh, or filling it with brownie brownie mix for sweet, sweet, delicious brownies. Yes, Patrick. Yeah. Okay. And that equidistant thing is the magic word because what did we just observe previously? The slope corresponded to the cross sectional area or the width, right? And so as long as if we want a constant slope, that means we need to have a constant width. But that doesn't mean that the shape has to be constant because what about if I drew some squirrely thing like this, right? So imagine it's like that. Would this still have a constant graph, even though it's a really weird old shape, right? Or I could be maybe less silly and just have well, okay, my art skills are not the best, but a slanty cylinder or slanty box or anything like that, wouldn't those also work? Okay, and why is it that they're working? Because what's true about the cross sectional length there, it's constant the entire way up and down. Now, if I make it non-constant, what's going to happen to my bottle graph? I won't get a straight line. Okay, and what was the assumption for this particular problem? That what kind of shape did we want our bottle graph to be? We wanted it to be a straight line, just for sake of example here. Okay, so again, we're kind of thinking backwards, and that's something that we're going to do tons of also. Okay, we no. Okay, so look at the next one here, number 4. Okay, so there we have two shapes, and it's a little hard to see on the printout, but you see how the cylinder and the straight line are kind of in a lighter shading, and then the curve and the thing that looks like a lampshade are kind of slightly darker. Okay, um, so would you buy that the total volume of the cylinder and of the lampshade are the same? Does it, just roughly speaking, look like that's possible? Okay. And so, in terms of the graph there that's to the left, how do we know, like, how is that fact that the volumes of these two guys are the same, how is that reflected in the bottle graphs? Yes. Yeah, they end at the same point. That tells you that they have the same total volume. And then does it make sense that they should also start at the same point? Because when they both have zero volume when you haven't put anything in them yet. Okay, so yes, does that make sense? Yeah. Okay. Um, so what about the stuff in between? Well, why is the cylinders one a straight line? Yeah, because the width is constant, right? That was what we just did a second ago. Okay, and why does the shape of the curvy part make sense as being what goes with the lampshade? Okay, because what's true about the lampshade? It's wider at the base and narrower at the top. Okay, so what kind of slope should we see early on in the curve? Gentle or steep? Okay, and what should we see towards the end? Steep, and it should be increasing from gentle to steep. Okay, okay, so um, there we go. Okay, now here's sort of a good question. Is there a point in time where the rate of filling or the rate at which H is changing is the same for both bottles? Okay, where?
Most likely in the middle.
Okay, most likely in the middle, but you can do better than that.
The width on both shapes.
Exactly, exactly. Where the width of the two things is the same. Okay. Now, you can. Does that make sense? Right. Where else would it be the same? The rates, not the heights. Okay. So not the start and the end, because so the rates here are corresponding to the slopes, not the y values. Okay. So do you see it's the only point at which they're the same is where the two bottles sort of intersect each other, or maybe another way of saying it, when they have the same cross-sectional length? Yeah. Okay. Now, looking at the curves to the left, where is the place? So let me just draw it here. Uh, so I'd have, say, this, oops, this, and this. Where is the point on the curvy part where the slope is equal to the straight line? It'd be somewhere like here, roughly, right, where the tangent is parallel to the other straight line, yeah, roughly speaking. Yeah, does that seem plausible? Yeah. Okay. And one of the major theorems from calculus is what demonstrates that this always is going to happen. Okay, and tell us under what circumstances it's going to happen, and then we'll have other tools that will allow us to find when this sort of thing happens in contexts that don't have anything to do with bottles. Okay, so does that kind of make sense? Yeah. Okay, so if you've got your computer with you, or an iPad, or heck, even your phone, right, or the classroom computer, so bust those open, and we're going to do some stuff with Desmos. Okay, so let me actually switch over to here. Okay, so now you guys, has anybody never used Desmos before? I think it's pretty popular in high schools now, right? Okay, it's not rocket science. What do you think I'm going to type in this little box here? Yeah, some function, right? So let me just do, for example, y equals x squared. So I'm going to do y equals x and then hit the square button and then hit enter, okay? And not shockingly, right, what do we get for the curve? Yeah, we get our handy dandy parabola, okay? And I think you guys would agree that this thing is not a straight line. Yeah? But what about if I zoom in on it? So pick a point, doesn't really matter. Like let's say this point right here, 1 comma 1. What's going to happen if I start to zoom in on this thing? What's true now? It looks like it's a straight line. Now, is it really a straight line? No, but it's really, really close to one. Okay. Now, I chose the point here 1 comma 1, and it may be a little hard to see on the screen, but 1 and 1 are right there and right there. Could we calculate what that slope is? Okay, roughly, right? Now, obviously, calculus will allow us to determine exactly what it is and without having to do any crazy arithmetic. Okay, but if I just said, like, if you guys walked in and I had this up there on the screen and I said, this is calculate the slope of this thing, and I hid the x squared part so that you didn't even know that I had actually secretly graphed a parabola. Okay, how would you compute the slope of this line? Well, how do you compute the slope of any line? Rise over run, right? Okay, so I need to do a rise over run computation. I've already got 1 point, 1 comma 1, and I picked that just to make the arithmetic easy, right? But if I go over to, say, this point right here, or this point right here, maybe that one's a little easier to see. All right, what's the rise between 1 and this point? Huh? 0.004. Okay. What about the run? 0.002. Well, I don't have to be a wizard with arithmetic to divide 0.004 by 0.002, and what should I get? I should get 2. Does that seem plausible just looking at the graph? A slope of 2. We? No. Okay. So, yeah, that seems plausible. Slope of 2 at that point. Now, do I know that it's really 2? How do I know it's not really like 1.999 or something like that? At this moment, do we have any way to verify that it's not 1.999 or 2.001 or something along those lines? No. I ballparked it here just by kind of looking at the graph, but that's not enough to really demonstrate that it really is 2. Okay, now it is, okay, but we will have to demonstrate that fact using extra tools. Um, right, okay. So could we play this game at any other point along this curve? Now, would we get the same answer necessarily? No, but let's do the same sort of thing. So zoom in on a random point, okay, and pick different ones, right? So don't all do the same thing, and compute the slope at your point in question, okay? And write down what your x coordinate is, what your y coordinate is, and what the slope you computed at that point is. Does that make sense? We? No. We. Okay. Play me in. And then we'll use that for the next thing. Okay, so I'll go back over here. Okay, so we just did this one, and then you guys will give me some other ones. Yes.
4, 2.
Okay, so you picked a point 4 comma 2. Oops. What'd you get for your slope? 4. Okay, did anybody else have that same point? Are you in agreement, or are you going to call BS? You agree. Okay, excellent. Anybody else? Oh, sorry. I wrote it backwards. Yeah. What were you going to say? Same thing? Man, you too. Whew. It's almost like you've had me before. You know how incompetent that I am. Okay. All right. What other point? Yes. Ah, okay. Good call. And what'd you get? -4. Okay. Anybody else have that same point? Yeah? Agree or BS? Agreed. Okay. Uh, and that's nice, right? Because the slopes don't have to be positive. Okay. Now, were they for our bottle graphs? Did the slopes have to be positive? Okay. And why was that the case with the bottle graphs? Yeah. Yeah, exactly. I'm filling the thing up. It's not as if there's like a leak in it or something. Okay. Um, yeah, that'd be a really weird looking bottle. Um, I don't know. Have any of you guys ever seen like those trick bottles where you fill them up and it looks like they actually drain? Uh, yeah. Yeah, so like maybe we could construct some really diabolical looking mechanism that would have that, but uh, or what is it called? There's like a name for these sorts of things, like a greedy cup, where if you tilt it too much to take a really big gulp of it, it actually like drains the liquid into a second reservoir, and so you have to like just sip at it. So yeah, we could come up with some evil mechanism. Okay, so but the slopes in general, not necessarily being tied to a physical object like the bottle graphs, could be negative, right? Is there a point where the slope is 0? Okay, what would that correspond to? Yeah, horizontal line, and in fact, not shockingly, it is at the origin in this case. Um, Now look at the graph. Does that seem plausible from the graph? Yeah, you guys seem in agreement? Okay, so we wrote here slope. What are we going to denote here? So let me actually change my labeling and say instead of X and Y, I'm going to think of this as A and F of A. Okay, so A is just whatever the particular X coordinate is. F of A is whatever you get when you plug it into the function, which for this particular one happens to be A squared because that was the formula. Okay, but how am I going to notate this idea of slope? Instead of writing the word slope, F prime of A. Okay, and so at a given point, the slope of the tangent line is F prime of A. Okay, now what we will learn, and those of you who have seen a little bit of calculus before, um, know that there are certain procedures that will allow us to get from a formula for a function to a formula for its derivative. Okay, but we're not there yet. Okay, and if anybody is like about to try and pull a power rule on me, das ist verboten. for now. Okay. Anyway. Okay. Now, what we can do with this, okay, is let me choose this point here. Okay. So I just chose the point 1 comma 1 for sake of demonstration. Okay. And if I want to compute the equation of a line that goes through that point and has the slope 2, then what's this top form here that I wrote? Y minus 1 equals 2 times x minus 1. What is that? That's the point slope form of a line, okay? And that is, for the most part, the one that we're going to use the most often in this class, precisely because we often know a point and a slope, right? So it's just the one that's most convenient. And so I just plug those things in, and of course I could solve it for mx plus b form if I wanted that instead. And so what I'm going to do now is go back over to Desmos. We already have x squared graphed. Let me also graph this guy. Okay, does that make sense? All right, so let's do that real quick. And so what did I say it was? 2x minus 1. Well, sorry, I need to y equals that guy. Okay, and then I'm going to kind of zoom in over here at my point. Okay, so the red curve is, of course, the original, the parabola, and the blue curve is the straight line 2x minus 1. And what do you notice at the point 1 comma 1 right here about the relationship between these two graphs? Yeah. Yeah, same slope, but they're also basically right on top of each other, right? And in fact, being able to tell the difference between the curve and the line is essentially impossible visually between, roughly here and here, right? They look almost identical. And that makes sense, okay? But what we can use with this is, so what is 1 plugged into my function? F of 1 is 1, right? That's easy. What about if I asked you to do like f of 1.5? What would you get for f of 1.5? It'd be, what's 1.5 times 1.5? If only you guys all carried around calculators in your pockets. I don't know. When you guys were in elementary school, did your teachers like, you're never going to have calculators all the time? Yeah, two and a quarter, right? 2.25. Okay, great. Uh, Now, was that all that hard to calculate? All right, but let's say you didn't actually have a calculator in front of you. Would that have been mildly annoying to have to sit down and do the arithmetic? Okay, it wouldn't have been horrible, but it would have been mildly annoying. Okay, so what I can do instead, though, is let's say that I don't want to know what the answer is exactly. I just want a ballpark. Okay, what would be another way that I could do this? Well, notice that the straight line and the curve are basically the same when I'm near to 1. What is true about as I get further away from 1? They get further apart. Okay. So what about if I plugged 1.5 into my straight line function instead of the parabola? Would the arithmetic be easier? Yes. Okay. Because what would I get? I'd get 2 times 1.5 is 3 minus 1, I'd get 2. Now, is that equal to 2 and a quarter? No, it's not. Is it pretty dang close? That's kind of a judgment call, right? but I can approximate it by plugging the x-coordinate into the straight line function rather than my curvy function. Okay, now, I picked 1.5 just for the sake of making the arithmetic easy to say. Okay, would that have been a wise choice here? Probably not. But what about if I did 1.1? Right? That would be basically looking at this point kind of right here. Is the answer I get by plugging into the blue function going to be pretty dang close to the answer I get if I plug into the red function? Are they going to ever be the same? No. There's only one place that they're same, and guess where that is? At 1. Okay, so the line and the curve perfectly agree at 1, and they start to diverge in their agreement the further away you get from 1. Okay, but is that good enough to get a rough estimation? Yeah. Okay, and turns out there's other ways that you can improve this estimation, which we'll talk about later. But yeah. Okay, so in terms of symbols, what we've just done here is what we've said is that near to the point a comma f of a, f of x is approximately equal to f of a plus f prime of a times x minus a. Okay, so let's think about what all that means. Okay, f of a is my height. F prime of a is what? What does that mean? Rate of change, or what's another word for that? Okay, what's another word for that? Slope. Okay, so the slope is a rise over run kind of thing. X minus A is a what? That's a run. So what happens if I multiply a rise over a run times a run? I get a rise, right? And f of a is a y coordinate, right? So if I say my y coordinate starts here and it changes by this much, that's my value. Yeah? That kind of makes sense? Okay, so what we basically just did here with with x squared and with the straight line is this equation, when we sorted it all out, was just 2x minus 1. Okay, that was the equation of my line. And we said that near to the point A, okay, which was in our example 1, I'm going to get roughly the same number if I plug it into x squared as if I plug it into the equation of that straight line. Okay, was it perfect? No, but that's okay. Sometimes an approximation is good enough. Okay, so does that kind of make sense? Right? So what we're doing here is using the fact that if we zoom in on a graph, it's roughly going to be straight as a means of approximating. Okay. Now, in some sense, this idea might be a little bit contrived because do you all carry calculators around in your pockets? Yes, actually, right? And so if you really wanted to know something, you could just punch it in and that's the end of it. Okay. But yeah, this idea will be handy in other respects. So, all right. Well, it is 8:50. Hope you've all had a wonderful week. Um, and just two quick reminders. Sunday night, I've got 2 assignments due. Really think of them as all part of the same assignment. I just broke it into 2 pieces for convenience. Okay. Those are going to be good things to do to review for the first assessment on Monday. Okay. Which will be over all of the sort of prerequisite kind of info. Um, as such, you do not have a warm up for Sunday because we're not doing class stuff on Monday. And Monday's assessment will be the only one that you do in class. So just come to class Monday and don't worry about anything else. Okay? And if you haven't already turned in your math autobiography, please do so. All right. See you guys next time.